Hello everyone and welcome to another lesson in probability and statistics for business. So today we will be talking about discrete probability distributions, and this is chapter 5. So first and foremost, what are our learning objectives for this particular lesson? Well, we have 5. We will be learning about the properties of a probability distribution. We'll be computing expected values, variances of probability distributions. We'll be calculating covariance and understanding its uses in finance, computing probabilities from binomial, hypergeometric, and Poisson, and how we use these distributions to solve business problems. So first and foremost, let's have a look at a few definitions, because the first question we have is, what is a random variable? So a random variable represents a possible numerical value from an uncertain event. Basically, if you have some uncertain event, you're trying to assign some value to it. Now, when you talk about assigning a value, you can think about this random variable in two perspectives. You can either think of it from a discrete value perspective or assigning continuous values. So that is why we have two concepts known as discrete random variables and continuous random variables. So where does this differ? A discrete random variable produces outcomes that come from a counting process. That is the important term here. Whereas a continuous random variable produces outcomes that come from a measurement or a measuring process. So for example, counting process, number of classes. You have 1, 2, 3, likewise. If you are talking about a continuous random variable, it could be your weight. Well, because your weight can be 62.5 kilograms, 62.57 kilograms. So it all depends on your measurement. So that is why we say we have two concepts, discrete random variables and continuous random variables. So based on that, we can divide these random variables, like I said before, into two concepts. So graphically, it would look something like this. Not exactly, but something like this. So you have a discrete random variable, that's why you have discrete bars, and you have continuous random variable. There's a certain continuity to it. Right, since we learned about these two concepts, let's have a look at a few examples. And let's try and identify whether it's a continuous random variable or discrete. The first one, the number of arrivals at an emergency room between midnight and 6 a.m. What I want you to notice here is it talks about the number of arrivals. So when you're talking about a number, you're actually counting. So there can be 1, 2, 3, 4, likewise. So then, can it be continuous? No, you're counting. Therefore, it's discrete. So this event can be signified under a discrete random variable. Then the second one, the weight of a box of cereal labeled 18 ounces. It's talking about a weight. So therefore, it arises from a measuring process. Hence, it is continuous. The third one, the duration of the next outgoing telephone call from a business office. What are they talking about? They're talking about time, duration. So that is also continuous. The fourth example, the number of kernels of popcorn in a 1 pound container. It arises from a counting process, number of kernels, discrete. And the last one, the average amount spent on electricity each July by a randomly selected household in a certain state. Talking about average amount spent, the money spent, right? So it can be $18.67, or it can be $19.5. That means $19.50. It's something which is not arising from counting but from a measuring process. So it is also continuous. So the important thing is, when you're given a variable, you have to identify whether it's a random variable, and then you have to segregate it into either discrete or continuous. Right, so this whole lesson I have divided into two sections so that it is easy for you to grab hold of the concepts. So in this particular lesson, we will be talking first about discrete random variables, and then we will be talking about probability distributions. So you might have a question as to why we are talking about discrete random variables only, because the concept of continuous random variables will be talked about in chapter 6. So this lesson has these two sections: discrete random variables and probability distributions. Right, let's have a look at discrete random variables first. So again, it can only assume a countable number of values. Let's have a look at a couple of examples. Let's roll a die twice, and what we are interested in is the number of times 4 occurs, right? So that is our random variable. So we are going to name this as x. Our random variable is labeled as x, and it is the number of times 4 occurs, right? So you're rolling the die twice. So how many times can 4 occur? Now you know that there are 6 numbers in a die on each side. Well, you can get 4 2 times. That is both the times that you roll the die. Or you can get it once. Or you might not get it at all. That's why you assign these values to x. 0, 1, and 2. And if you notice, these arise from a counting process. Hence why you assign 0, 1, and 2. That is why x here is a random variable which is discrete. Let's have a look at another example. You're tossing a coin 5 times, and what you're interested in is the number of heads that you get. Well, if you toss a coin 5 times, you might not get heads even once. You might get tails all the time, or you might get heads all 5 times, or any number in between, right? So if you notice, this again arises from a counting process: 0, 1, 2 to 5, and you're assigning these values to this random variable x, right? So x here is a discrete random variable. So we talked about the discrete random variable. Now we are a bit more interested in this probability distribution. We are interested in a probability distribution for a discrete random variable. What is this? So first and foremost, let's have a look at what this means. A probability distribution for a discrete random variable is a mutually exclusive listing. Remember what mutually exclusive means? It means you cannot several events which cannot occur at the same time. Listing of all possible numerical outcomes for that variable and a probability of occurrence associated with each outcome. So you have a listing of mutually exclusive outcomes, numerical outcomes for a particular variable. So let's take the variable as the number of tuition classes you attend during grade 10 or 11, right? Let's say you attend from minimum of 0, that means you don't attend tuition classes, to a maximum of 9 tuition classes. So you have the variable defined as tuition classes, and your outcomes, your numerical outcomes are 0, 1, 2, 3 up to 9. And then you're assigning a probability to this. So what is the probability of students not attending any tuition classes? Let's say it's 20% or 0.2. What is the probability that students attend 9 tuition classes? Let's say 5% or 0.05. Likewise, to a particular variable which we defined as tuition classes, you have several outcomes, right, which are mutually exclusive listing of all the numerical outcomes from 0 to 9, and you're assigning a probability to it. So something like this, the number of classes taken, 2, 3, 4, 5, and the probabilities are assigned to it. Let's take another example.
So let's have a look at the probability distribution pertaining to a discrete random variable. So in this particular example, what I'm taking is I'm tossing 2 coins, and my discrete random variable x is the number of heads. Why am I considering capital X as a discrete random variable? Because you're counting the number of heads. So you're tossing 2 coins and you're counting the number of heads. So what are the outcomes that you can get? The first coin can be tails, the second coin can be heads. That's one outcome. The first coin can be heads, the second coin can be tails. Both coins can be heads or both coins can be tails. So these are the 4 possible outcomes. You can either get both tails. In the first coin you can get a tail, second coin you get a head. Likewise, you have 4 outcomes. Then you have to check what are the probabilities pertaining to each outcome, right? So this is the table regarding that. So the x value, that is the number of heads, can be 0. Here, the first outcome, you have no heads. Or it can be 1. Likewise. So out of 4 outcomes, there are 2 possible outcomes where you have 1 head. Then x can be 2. That is the number of heads can be 2. So out of 4 outcomes, there is 1 possible outcome where both coins are heads. So what are the probabilities pertaining to each x value? 0 heads. Well, there is 1 out of 4. That is why you have 0.25. You have 1 head. That there are 2 possible outcomes out of a total of 4 possible outcomes. So you have 2 divided by 4.5. And then the number of heads being 2, there is only 1 possible outcome out of a total of 4 possible outcomes. That is why you have 1 divided by 4.25. So these are the probabilities assigned to the corresponding x value. Accordingly, you can draw the graph where on the x-axis you have capital X, that is your discrete random variable, and on your y-axis you have the probability value. So when x is 0, your probability is 0.25. When x is 1, probability is 0.5. When x is 2, probability is 0.25. So this is what the probability distribution would look like for this particular example. Now, let's have a look at a very important concept. With regards to discrete random variables, we want to check what is the expected value, or in other words, the mean value of a particular discrete random variable. So that is given by, you take the particular value, xi, the ith value, and you multiply it by the associated probability to it. So that is how you get the expected value or the mean value of a discrete random variable. Let's have a look at an example which we did previously. So the example of tossing 2 coins and you're checking for the number of heads. So this was the table we obtained. So how do we get the expected value or the mean according to this equation? Very simple. What this is telling me is, take the data point, okay, 0, and then you multiply it by the probability assigned to it, 0.25. Right, and then you add the second data point, because you have the sigma notation here. You notice you have the sigma notation. So you take the second data point and you multiply it by the probability assigned to it. You take the third data point and you multiply it by the probability assigned to that. And you take the summation of all of that and you get the expected value. So that is what I've done here. 0 into 0.25 plus 1 into 0.5 plus 2 into 0.25. All of this equals 1. So 1 is the expected value of capital X, or in other words, the expected value of the number of heads would be 1. Then we check the mean value, how to get the mean. Now we are looking at how to get the dispersion. So that is variance and standard deviation of a discrete random variable. So the variance is obtained by this particular equation, where you take the ith value of capital X and you deduct the expected value of capital X, you square it and you multiply it by the probability assigned to it, and you take the summation. So this is how you calculate the variance. To calculate the standard deviation, you simply take the square root of this. And then we have covariance. So up to now we talked about calculating the mean, variance, standard deviation for a discrete random variable. Now we are looking at covariance. So covariance measures the strength of the linear relationship between the two random variables x and y. So it measures the linear relationship, the strength of the linear relationship, strength. So if you get a positive answer, that would mean your x and y would have a positive relationship. So what does it mean? If your x is increasing, y would also be increasing. If x is decreasing, y would also be decreasing. That is why you say a positive relationship. Both move in the same direction, either increasing or decreasing. But if you get a negative answer, a negative covariance means a negative relationship. If x is increasing, y is decreasing. If x is decreasing, y is increasing. So there's a negative relationship. So that is given by this particular equation. The covariance of x and y is given by the data point pertaining to x minus the expected value of the discrete random variable times the data point pertaining to y minus the expected value of capital Y times the probability of xi and yi. So let's look at an example. Let's see how we calculate the mean, standard deviation, variance, and covariance when it comes to an example pertaining to discrete random variables. So in this example, you're given, consider the return per $1,000 for two types of investments. So these are the returns that are given for two types of investments, right? Return per $1,000. You're given the economic condition and the probability of that economic condition. So a recession, there's a probability of 0.2. For a stable economy, there's a probability of 0.5. And for an expanding economy, there's a probability of 0.3. There are two types of investment, X and Y. The returns pertaining to it are given here, negative 25, negative 200, positive 50, positive 60, 100, 350. Now let's see how we calculate this.
Right, so how do we calculate this? So we are given the table and we are first asked to calculate the expected value. Let's see how we calculate the expected value, because then we will know the average amount of return from fund X and fund Y. And afterwards we'll see and calculate the standard deviation, because from that we will get some idea of the risk each fund poses. Right, so how do we calculate the expected value? The expected value of fund X. Well, you take the data point negative 25 and you multiply it by 0.2, plus you take the data point $50 when there's a stable economy, the probability of that is 0.5, plus $100 is the return when you have an expanding economy, and the probability of having an expanding economy is 0.3. So 100 into 0.3. And when you calculate the summation of all of this, you will get the answer as $50. So on average, if you were to invest $1,000 in fund X, you would get $50. What is my expected value of fund Y? Minus 200 when there's a recession. What is the probability? 0.2. So minus 200 into 0.2 plus $60 when there's a stable economy which has a probability of 0.5. 60 into 0.5 plus $350 return when there's an expanding economy which has a probability of 0.3. So 350 into 0.3. All of this totals up to $95. So if you were to only look at these two, it is quite obvious that you should invest $1,000 in Fund Y. Why is that? Because you earn on average $95 from Fund Y. But there's something else that we have to consider. That is the dispersion or the risk associated with these two funds. So how do we calculate that? We have to look at the standard deviation. So the symbol that we use is sigma x. This is the standard deviation of x. How do we do that? We take the point minus 25, and from that we deduct the average pertaining to fund x or the expected value, which is 50. We square it and then we multiply that by the associating probability 0.2 plus the next one. The point is $50, and from which we deduct the expected value of x, which is 50, square it. What is the probability associating to this data point? 0.5 plus the third data point is 100 minus the expected value of x is 50, square it, and then you multiply that by the probability 0.3, and then you take the square root. Don't forget this because we are considering the standard deviation, and when you calculate this you will get the answer as 43.30. And similarly, the standard deviation pertaining to Fund Y is calculated as, you take the first data point minus 200, you deduct the expected value of Y, which is 95, you square it and multiply it by 0.2 plus second data point is 60, deduct the expected value of Y, square it into 0.5 plus third and final data point 350 minus the expected value of Y squared into 0.3. Since we are calculating the standard deviation, we consider the square root, from which we get the answer as 193.71. So here, if you look at these two figures, you notice that the standard deviation pertaining to Fund X is less than the standard deviation pertaining to Fund Y, which tells us although on average Fund Y provides a higher return, there's a higher risk because it's 193.71 pertaining to Fund Y. Now, we can also calculate the covariance, that is to see what is the relationship between Fund X and Fund Y. So, let's calculate the covariance, which is given by sigma xy, right? So how do we calculate this? You take the first data point 25, deduct the expected value of x, this is the first data point pertaining to x, times the first data point pertaining to y minus 200, you deduct the expected value of y 95, times the probability associated to those first data points is 0.2 plus the second data point pertaining to Fund X is 50 minus the expected value of x is 50 into the second data point pertaining to y is 60 minus the expected value of y 95 into the probability associated with these two data points is 0.5 plus the final third data point associated with x is 100 minus the expected value of x is 50 into the data point pertaining to y 350 minus the expected value of y into 0.3. When you calculate this, you will get an answer, positive answer 8250. So you have got a positive, large positive answer for covariance.
So according to what we calculated, we got the mean, the variance, standard deviation, and the covariance. So the mean value for the expected value of, or the expected value of x, we obtained as 50 using the equations that we learned. Then the expected value of y we obtained as 95. And how did we interpret this? So fund X is averaging $50 return and fund Y is averaging a $95 return per $1,000 invested. So this 50 is telling you, look here, you have on average chance of earning $50 for every $1,000 you invest in fund X, but you have a chance on average to earn $95 for every $1,000 that you invest in fund Y. So if we were to only look at these two numbers, obviously an investor would invest in fund Y. But there is a catch. What about the risk associated with these investments? That is measured by what we calculated under dispersion, the variance and the standard deviation. So we need to look at those numbers as well. So once we calculated them, we got these answers, which told us the standard deviation of X was 43.30, but the standard deviation of Y was 193.71. So obviously the standard deviation of Y is much higher, almost more than 4 times higher than the standard deviation of X, which means the risk in fund Y is almost more than 4 times the risk of fund X. So that is why you are naturally getting a higher return. So as you know, higher the risk, higher the returns. Right. Then we have a look at the covariance. That is the strength of the relationship between X and Y. So when you calculate the covariance using the equation that was given before, we get a large positive answer. So how do we interpret it? So since it's a large positive answer, we know that there's a positive relationship between X and Y. That means if there's an increase in X, there's an increase in Y. If there's a decrease in X, there's a decrease in Y. These are all very valuable information for an investor when you're considering these two funds, X and Y. So this slide I have put here for your information. So all this time we were talking about calculating the expected value of X independently. We only calculated the expected value of one particular discrete variable. But what if you have two variables? So here we are calculating the expected value of X plus Y. What is the answer? It's given here by this expression, expected value of X plus the expected value of Y. The variance of X plus Y, sum of two random variables, is given by the variance of X plus the variance of Y plus 2 times the covariance of X and Y. And the standard deviation is simply the square root of this equation. Right, so that was a little bit of a brief introduction to discrete random variables. Now let's have a look at the next section of chapter 5, which is probability distributions. So under probability distributions, we will be looking at discrete probability distributions in this particular chapter. In chapter 6, we will have a look at continuous probability distributions. So all this time we were talking about discrete random variables. So pertaining to discrete random variables, we have discrete probability distributions, which we are talking here. I will be focusing only upon the binomial and the Poisson. Hypergeometric I will not be focusing. And these continuous probability distributions will be talked about in the next chapter. Right, so these are the two discrete probability distributions that we will be talking about, the binomial probability distribution and the Poisson probability distribution. So let's have a look at the binomial probability distribution. So let's have a look at some of the properties pertaining to this binomial probability distribution. So it has a fixed number of observations. For example, 15 tosses of a coin, 15. 10 light bulbs taken from a warehouse, 15 tosses of a coin. That means it has a fixed number of observations. These observations can't change. Then each observation is categorized as to whether or not the event of interest occurred. It is very important. So it is categorized as to whether or not the event of interest has occurred. which means it's categorized into two. That is why we call it binomial. You have two categories. Binomial, bi means two. So, for example, a head or tail in each toss of a coin, head or tail, defective or not defective. Do you see? It's category. The event of interest is defective light bulb or a not defective light bulb. Event is heads or the other event is tails. It's categorized into two. So we learned two properties now. The number of observations are fixed and each observation is categorized into two, whether or not the event of interest has occurred. Now, in this case, these two events are mutually exclusive and collectively exhaustive. So the probability of the event of interest occurring, we take it as pi. And the probability of event of interest not occurring is 1 minus pi. Now, the important fact here is this pi remains a constant for each observation. So it doesn't change. That is very important to remember. The pi that is the probability assigned to each event remains a constant for each observation. So for example, if you take the probability of getting a tail, so you're tossing a coin, the probability of getting the tail is same each time you toss the coin. That is 50. There's a 50% chance of 0.5 probability if you're getting a tail and 0.5 probability of you getting heads. It does not change for each observation. And the observations are independent, which means if one particular event has no impact or there's no direct link between two events, so it is independent. Just because a computer crashes, say, on Wednesday, that has no impact on a computer crashing on Thursday. The two computers that crashed on these 2 days are independent of each other. So these are properties pertaining to binomial probability distributions. Fixed number of observations, each observation categorized into the event of interest occurring or not occurring, and then the probability assigned to each event of interest remaining a constant, and then these observations being independent. So where do we use this? That's the next question. That's why we talk about the applications. So let's look at the applications. A manufacturing plant labels items as either defective or acceptable. So you see, there are a fixed number of items. These items are categorized into the event of interest occurring or not occurring. So not occurring would be, let's say, defective, and occurring would be acceptable. And then the probability assigned to these events should be constant, and it should be independent. Then another example. A firm bidding for contracts will either get a contract or not. A marketing research firm receives a survey response, yes, I will buy, or no, I will not. And finally, new job applicants either accept the offer or reject it. So these are some of the applications where you use binomial distributions. Now, a very important thing that we have to keep in mind is the counting techniques pertaining to binomial distribution. Now, why are we learning this? Because in the next slide, we will learn the probability distribution function pertaining to binomial distributions. And in that function, you will come across this counting techniques expression included in it. So let's take an example. Suppose the event of interest is obtaining heads on the toss of a fair coin. You are to toss the coin 3 times. In how many ways can you get 2 heads? Right, so this we have to identify, okay, we are talking about tossing a coin, and the question asks how many ways can you get 2 heads? It's a counting process. So that means we are using some kind of a discrete random variable, and then hence we are talking about discrete probability distributions. So up to now we have talked about only about binomial distribution. So definitely the binomial probability distribution is used in this particular example. That's how you come to that conclusion when you're given this question. Then you have to have a small picture in your mind. So they're tossing the coin 3 times, and how many ways can you get 2 heads? Well, you can get the 2 heads in the first 2 times, or the second and third time, or the first and third time. Likewise, the first 2 times you get heads, or the first and third time you get heads. In between you get a tail, or the second and third time you get heads. So there are 3 ways you can get 2 heads. Now this is very simple. Now we are just asked how many ways can you get 2 heads. There are 3 ways. It's very straightforward. But if you are given a much more complicated situation, how would you calculate this? For that we use this particular expression. Now if you had a look at the previous lesson, we talked about counting rules, and under counting rules, counting rule number 5, we talked about combinations. So that is what we are using here, and that is why we learned about combinations in that particular lesson, because we are using that in this chapter. So pertaining to binomial distributions, the counting technique we use is the combinations expression, the expressions pertaining to combinations. Out of n objects, if you were to select x objects, what are the number of ways of selecting those x objects is given by this expression. So you have n objects. Let me repeat that again. You have n objects, and how many ways are there to select x objects from those n objects is given by this expression. N factorial, that is the total number, divided by x factorial, that is the number of objects you are selecting, times n minus x factorial. Now what is n factorial? N factorial is given by n times n minus 1 times n minus 2 times up to 1. Substitute n by 5. So you have 5 factorial. How would you write that? 5 into 4 into 3 into 2 into 1. Likewise. So let's look at a very basic example. How many possible 3-scoop combinations could you create at an ice cream parlor if you have 31 flavors to select from? So you have 31 flavors in total. That means n is equal to 31. And you're asked how many possible 3-scoop combinations could you create? So that means you're selecting 3. So your x is 3. So out of 31, how many ways are there for you to select 3? That is given by the particular equation. We can use the equation n is 31, x is 3. You directly substitute the numbers and you get the answer as 4,495. Now, I ask you to go back to the previous chapter and see how this is calculated, what this actually means, and also refer to more material online, because here we are directly using the equation. But it is very important for you to understand what this expression means. So we had a look at how the counting process works. Now let's look at the probability distribution function pertaining to binomial distributions. So this is a very long equation, but if you notice this particular this part of the equation, this is the counting process, right? This is actually NCX, and then this value is multiplied by the particular probability pertaining to the event of interest and the number of times the event of interest occurs into 1 minus pi, which is the probability of event of interest not occurring. Or else we can look at it in a way where we say the complement of the event of interest to the power n minus x. So this here talks about the counting, and here you're given the probabilities of events of interest, right? So this is the equation for the binomial distribution equation. So if we were to look at a small example, so this question asks us, what is the probability of one success in 5 observations if the probability of an event of interest is 0.1? So what are the important facts here? They're talking about what is the probability of one success. That's the question. What is the probability of one success and you're given 5 observations, and you're told if the probability of an event of interest is 0.1. So let's have a look at how we solve this.
So how do we go about calculating this? Well, it says what is the probability of one success in 5 observations if the probability of an event of interest is 0.1. What is the probability of one success, right? In 5 observations, okay, if the probability of an event of interest is 0.1. What is the event of interest? This success, some kind of something which is successful. So first we note down my simple x is 1. It is the one success. And then I have 5 observations. So n equals 5. And the probability of event of interest is pi, that is 0.1. So what is my probability distribution function pertaining to binomial distributions? Well, it is probability of x equals 1, given that I have 5 observations with event of interest, the probability of an event of interest is 0.1. This is given by ncx times this multiplied by pi to the power x multiplied by 1 minus pi to the power n minus x. So this is multiplication and this is x, don't mix the two up. So ncx is given by n factorial divided by x factorial times n minus x factorial times pi to the power x 1 minus pi to the power n minus x. So all we have to do now is substitute in the numbers. So here we have 5 factorial, 1 factorial, 5 minus 1 factorial, 0.1 to the power 1, 1 minus 0.1 to the power 5 minus 1. So 5 factorial can be written as 5 times 4 times 3 times 2 times 1 divided by 1 factorial is 1 into 5 minus 1 is 4 factorial, so that is 4 into 3 into 2 into 1 times 0.1 to the power 1 is 0.1 times 1 minus 0.1 is 0.9, so 0.9 to the power 4. This cancels off, and when you calculate this you will get 0.32805. So that is the probability of one success in 5 observations if the probability of being successful is 0.1, and that is how you calculate this.
Right. So when we are solving it, we note down that x is equal to 1. That is what we want, one success. And there are 5 observations. That is why n is equal to 5. And the probability of an event of interest is pi, which is 0.1. Now we simply substitute these numbers into the probability distribution equation, and we substitute the numbers and we get the answers at 0.32805. So n is 5, so 5 factorial, x is 1, 1 factorial, 1 factorial is 1, and here you get 5 minus 1 is 4 factorial, and so when you calculate this part, you are remaining with 5, right? Because 4 factorial cancels off with, here you get 5 times 4 factorial, and here it is 0.1, which is the probability of an event of interest, which is one success. So you have the question asks only for what is the probability of one success times the probability of event of interest not occurring, which is 1 minus 0.1, 0.9 to the power of 5 minus 1. So that is how you get 0.32805. So that is how we calculated the binomial distribution algebraically. Graphically, this is what it would look like. Now here the important fact is the shape of the binomial distribution depends on 2 things: the probability of event of interest pi and the sample size n. So as you can see here, the sample sizes remain the same, but the probability of event of interest has increased. So when the probability of event of interest has increased, if you notice the shape here has changed, right? So some of the characteristics pertaining to binomial distribution, the mean value is given by the sample size into the probability of event of interest. The variance is given by the sample size into the probability of event of interest into the probability of event of interest not occurring, right? So the standard deviation is simply the square root of it. So an example here, if you notice, now probability of event of interest here is 0.1 and here it's 0.5, but if you notice, because of that change the mean has increased, and also because of that change the standard deviation also has increased from 0.67 to 1.118. So because of these particular changes, right, the shape of the distribution has changed. So that is the binomial probability distribution. Now let's have a look at the Poisson probability distribution. So the Poisson probability distribution, you are using it when you are interested in the number of times an event occurs in a given area of opportunity. So the number of times an event occurs in a given area of opportunity. What do you mean by this given area of opportunity? Well, it is a continuous event. Given area of opportunity is a continuous unit or interval of time, volume, or any such thing, right? For example, you can have a look at the number of scratches in a car's paint. So the car's paint, you can consider a certain area of the car, and you're considering the number of scratches. Then if you take the number of mosquito bites on a person, so you can consider, say, a particular area, body area, say the arm, and the number of mosquito bites on that particular area in the arm. And then another example, the number of computer crashes in a day. So the area of opportunity here is time. So in a particular day, the number of computer crashes. So you apply Poisson distribution. When do you apply this Poisson distribution? When you want to count the number of times an event occurs in a given area of opportunity. It's fairly obvious because that's what we looked at before. The probability that an event occurs in one area of opportunity is the same for all areas of opportunity. That is very important to keep in mind. Let me read that again. The probability that an event occurs in one area, the probability in one area should be the same for all areas of opportunity. That is important. The number of events that occur in one area of opportunity is independent of the number of events that occur in the other areas of opportunity. And then the probability that two or more events occur in an area of opportunity approaches zero when area of opportunity becomes smaller. And the most important fact, this should be the most important one, the average number of events per unit is, we call it lambda, the average number of events per unit. So now when you consider this here, the probability that an event occurs in one area of opportunity is the same for all areas of opportunity. Consider the previous example of computer crashes in a day. So take a number of computer crashes on Monday. So the probability of that event occurring, the same probability should exist for the number of computer crashes occurring on Friday. The probability of event occurs should be the same in that particular day, right? Because it says probability that an event occurs in one area of opportunity is the same for all areas of opportunity. So in that particular day, in Monday, the probability of during Monday, the probability of number of computers crashing should be the same as during the day of Friday, the probability of number of computers crashing. And it should be independent. So the number of computers crashing on Monday should have no impact whatsoever on the number of computers crashing on Friday. And as the unit area of opportunity decreases, so that's what we are saying here, area of opportunity becomes smaller. So we are not considering a day, we are considering a minute, a second. So that area, the time, or in this example's case, the time becomes smaller, the probability that two or more events will occur will be 0. So that means in a small area of opportunity, there is only one event that is occurring. Two or more events occurring in the same unit, same or at the same point of time is 0. And the most important fact is the average number of units per unit, average number of events per unit is given by lambda. So taking this all into consideration, the Poisson distribution formula. So we had a look at the binomial distribution formula. Now the Poisson distribution formula is given by this equation. E here is the exponential function to the power minus lambda, that is the average number of events occurring per unit, average number of events occurring per unit, times lambda to the power x divided by x factorial. So this is the probability distribution pertaining to Poisson distribution. So some of the characteristics, like we looked at binomial distribution, the mean in the Poisson distribution is given by lambda, and also the variance is also given by lambda. So it's very easy to keep in mind. So the standard deviation is simply the square root of the variance. Now, just like the shape of distribution for the binomial distribution, which depended upon the probability of event of interest, which is I, and the sample size n, in this case, the shape of the Poisson distribution depends on the parameter lambda. So as lambda increases, you can see how the distribution changes. So these are the two distributions that I wanted to talk about under discrete probability distributions, which is one is binomial probability distribution and the other one Poisson probability distribution. So all this time we were talking about probability distributions and more specifically discrete probability distributions. We also talked about discrete random variables. So the continuous part we will talk about in the next chapter. So the chapter summary, we talked about probability distributions of a discrete random variable. We talked about covariance and its applications. We talked about binomial distribution. We talked about Poisson distribution. So that is it for today. Thank you very much, and I hope you have a productive day.